Alright, so today we're going to do a problem on the Arzelà-Ascoli Theorem. So we see that we are given the conditions, we got a space of continuous functions, we got a compact metric set, we got a, we don't know if it's pointwise bounded, we don't know if it's equicontinuous, but we have that G sub n, which is, we want to find if it has a uniformly convergent subsequence, right? So we're going to be applying Arzelà-Ascoli on G sub n. Well, we know that 1, K is compact. That's true, 0, 1 is compact. And then next, we know that G sub n is the set of like continuous bounded functions with domain 0, 1 because f, right, when we integrate, f is bounded, it's continuous, and it's on 0, 1. And when we integrate that by the fundamental theorem of calculus, we'll also get that G sub n is complex valid continuous bounded with domain 0, 1. Okay, now let's show that it's pointwise bounded. And in order to show that it's pointwise bounded, we're going to show that it's uniformly bounded. So let's look at what's inside the integral. So sub n, conjugating this, we can multiply the top and bottom by f sub n t plus n squared plus n, or f sub n t plus n squared plus n. Difference of squares, and we get that that is equal to f sub n t plus n squared minus n squared over square root f sub n t plus n squared plus n. These cancel, we get that that's equal to f sub n t over square root f sub n t plus n squared plus n. And notice that since f sub n is bounded above by 1, this is bounded above by 1 over, and notice that this denominator, the smallest that this can be is 0, and we see also that it's going to be less than or equal to 0 plus 1. Oh, sorry. So when this is bounded above by 1, this would be 1, and then the smallest that this is like bounded below by 0, since n has to be a natural number, right? So that's going to be this, the smallest this can be is 1. Or it can't even be 1 actually. So it's bounded above by 1. And thus we have that this integral, right, is bounded above by, this whole thing is bounded above by 1. And notice that x can only range from 0 to 1. So it's actually bounded above by the integral from 0 to 1 of 1 dt, which is equal to 1. All right, so we have that it's uniformly bounded, since for all n, this thing is bounded above by 1, which is in the reals, so it's uniformly bounded and thus pointwise bounded. Okay, now let's show that it's equicontinuous. Once we do that, we can basically just get to our conclusion. Okay, so why is this function equicontinuous? Well, we can just use the mean value theorem, right? So by MVT, for all x, y in 0, 1, we have gn of x minus gn of y is equal to gn prime of c times x minus y. And notice that by fundamental theorem of calculus, g prime of this is just equal to g prime of c for all, or g prime of x actually. G prime of x is equal to square root f sub n x plus n squared minus n. And this whole thing is bounded above by 1, as we showed. And since c is anything from 0 to 1, so it's any x in our domain, we know, or I guess it should be between x and y are both in our domain. We know that this whole thing is bounded above by x minus y. So we see for all epsilon greater than 0, letting delta equal epsilon, we get that x minus y less than epsilon, less than delta, which is equal to epsilon, implies that g sub n of x minus g sub n y is less than epsilon for all n, right, for all x, y in our domain. And we're done. So we showed all these 4 conditions of the Arzelà-Ascoli theorem, and thus we know that G sub n contains a uniformly convergent subsequence.